In this video, we're going to have a look at implicit differentiation, what it is, why we need it, and how to work with x's and y's in a derivative. So up to this point, we've been differentiating quite complicated functions at times, but we started with our basic polynomials, and we have examples such as this, 4x squared plus 3x to the power of 4. Now this notation is telling us to differentiate 4x squared with plus 3x to the 4 with respect to x. And that means we can use our rules of differentiation on any x terms in the expression, but certainly no y terms, of which there are none in this example. So we'll use our rules for differentiation. We'll bring the power down and drop the power by 1. 2 times 4 is 8, drop the power by 1, power of 1. And then we've got 12x cubed. So we've differentiated this function with respect to x, which means that all the x terms have had the rules of differentiation applied to them. This second example, we're asked to differentiate 4y cubed minus 6y squared with respect to y. And again, that's fine. That means we can use our rules of differentiation on any of our y terms, but certainly no x terms. So differentiating with respect to y means we can use the rules on y terms. Differentiating with respect to x means we can differentiate with our x terms. But you may have been wondering at some point up to this stage, what happens if I'm asked to find the equation of a tangent to a circle? And a circle equation, as you know, has x terms and it has y terms. So we need to be able to differentiate with respect to x and or y, but generally with respect to x, a circle equation. And I'm going to work through an example which looks at what we do when we differentiate y terms and why we do it. I'm going to do it 2 different ways. Okay, the first way I would say you're never going to do this. When we differentiate this circle equation, we're never going to do what I'm about to do. We're never going to expand the brackets and collect like terms together. There's just no point in doing it because we know a rule for differentiation that makes life a lot easier. So I will go through this example again using that rule in just a few minutes. So first of all then, I'm going to expand all of my brackets and see what happens. So I'm doing d by dx of x squared minus 4x plus 4 plus y squared minus 6y plus 9 equals 25. So I'm going to differentiate all of this, which let's collect the like terms together. We end up with x squared plus y squared minus 4x minus 6y, and then we've got plus 4 plus 9, we've got plus 13. I'll take that 13 across to the other side, and we've got equals 22. Now, it's almost like we've worked backwards in a circles question, haven't we? Because quite often you're asked to convert this form into this form. Yeah, what we've done is work backwards. So we need to differentiate each of the terms in this equation with respect to x. Now it's going to be problematic whenever we have something to do with y, but we'll have a quick look and see what happens when we do this. I will just change that to 12 because, as you all know, and are probably screaming at the screen, that should be 12. Okay, we're going to differentiate x squared, we're going to differentiate y squared, we're going to differentiate 4x, we're going to differentiate 6y, and we're going to differentiate 12. Okay, so differentiating this whole thing means differentiating each term individually, which is what you've always done. So this is probably not going to be too much of a problem. It's going to be 2x. This is not going to be too much of a problem. It's going to be minus 4. This isn't going to be too much of a problem because if you differentiate a constant, you get 0. But these 2 terms are going to cause us a problem or 2. So I'm going to have a look over here at what happens when we differentiate these. So if I'm asked to find d by dx of y squared, I can't differentiate y squared with respect to x I can differentiate y squared with respect to y, however, just like we did in the earlier example. So I could find d by dy of y squared. And then if I use a little bit of trickery, I will be able to write down what it would be if I differentiated with respect to x. Now let's have a look at what I've just written. This is one of those instances, and there are a few in the A-level course, where dy by dx, or d by dx, or d by dy behave like fractions. They are not fractions. It must be stressed, they are not fractions. But their notation makes them appear like fractions, and we can use properties of fractions to enable us to simplify things down. So if I said I know I can differentiate y squared with respect to y, I'd be finding d by dy of y squared. If I then multiply that by dy by dx, you can think of this as multiplying this fraction by this term by this fraction. And if we do that, you will notice that the dy up here cancels with the dy down here. Okay? And that means what we're left with is d by dy of y squared is 2y, and then we have to multiply that by dy by dx. d by dy of y squared is 2y, multiplied by dy by dx, because this is the same as d by dx of y squared. So let's have a look at that in practice then for the next term that we've got, which is the 6y. So again, we can say d by dy of 6y, which we can do. And then as long as we multiply that by dy by dx, then we're good to go. So what we have then, d by dy of 6y is 6, and we have to multiply by dy by dx. Now the shorthand here, the thing that's actually happening that you can take forward into every example that you're going to do, is when you differentiate a y term with respect to x, you must differentiate as you would ordinarily, so that y squared becomes 2y. But remember to multiply by dy by dx. The reason we multiply by dy by dx is here. So let's go back to our example. D by dx of x squared is 2x. D by dx of y squared is this, 2y times dy by dx. D by dx of 4x is 4. D by dx of 6y, 6 multiplied by dy by dx. And d by dx of 12, as we said earlier, is 0. When you differentiate a constant, you end up with 0. Now we'd like an expression for dy by dx. And we do that by manipulating our algebra. We just take terms to the left, to the right, whatever comes out. So we've got 2y dy by dx minus 6 dy by dx equals 4 minus 2x. We can factorize. And then we can divide. And then we have an expression for dy by dx. Now, this expression for dy by dx does utilize x and y as you would expect. And so if we're to calculate the gradient at a certain point, we're going to need an x coordinate and a y coordinate to do so. And that, in a nutshell, is implicit differentiation. Whenever you differentiate a y, do it normally, but remember to multiply by dy by dx. This is the reason why. Now, I did say a minute ago that you wouldn't normally differentiate that circle equation the way that I just did it, and that's absolutely true. So I will show you in just a second how I would do it using the chain rule. So using the chain rule for differentiation, this is made a lot easier as long as we remember that when we differentiate a y, we multiply by dy by dx. So if we differentiate x minus 2 squared, so this is what we're doing effectively now, d by dx of x minus 2 squared plus d by dx of y minus 3 squared equals d by dx of 25. So we can do that using the chain rule, can't we? So if we differentiate x minus 2 to the power of 2, we end up with 2 of x minus 2, and we would be multiplying by the derivative of what's in the bracket. The derivative of what's in the bracket is 1, so we've just got 2x minus 2 to the power of 1. If we differentiate this bracket, we'd end up, remember, we're differentiating y normally, but remembering to multiply by dy by dx. So we would end up with 2 lots of y minus 3 to the power of 1. And then differentiating the bracket as per the chain rule, we would be multiplying by 1. And then we have to remember, because we're differentiating a y, we're multiplying by dy by dx. And if you differentiate 25, you get 0. And if we do, again, our rearranging, then we've got dy by dx equals this. So we've got minus 2 lots of x minus 2 divided by 2 lots of y minus 3, which is 4 minus 2x. I'm going to skip to the end. 4 minus 2x over 2y minus 6, which is what we got when we differentiated it the long way. So this is how you would differentiate this function if you were ever asked to do so. The reason I did it the long way first was to really illustrate what's happening when we differentiate a y term. So hopefully you've got the principles there of implicit differentiation. This is the type of question that would be asked. So we've got this curve, 2x squared minus 3xy plus y squared equals 12. So we're find an expression for dy by dx, find an equation for the normal. So we're going to differentiate each of these terms, 2x squared minus d by dx of 3xy plus d by dx of y squared equals d by dx of 12. Now, I should say, it's not required to write d by dx of each term as you go. The reason I'm doing it just for now, and it's not even something I do in my work, if I'm completely honest, the reason I'm putting it in there for now is because I want to draw attention to some of the terms that we've got, and in particular, what I want to draw attention to is this one, the 3xy, because we know how to differentiate 2x squared, we know how to differentiate y squared now, differentiate as normal, multiply by dy by dx, but this 3xy could prove problematic. So what we have here, and it's a fairly common thing for examiners to throw in, is we have an x term multiplied by a y term, and that's the key part of this. We have something to do with x multiplied by something to do with y. So we need to use the product rule. So for the product rule, we're going to say that u is our 3x. We're going to say that v is our y, 3x multiplied by y. If we differentiate u, we just get 3, and if we differentiate y, we end up with 1 multiplied by dy by dx, which, as you can see, is just dy by dx. Okay, which makes sense. It's differentiating y with respect to x. So if I differentiate this together, I've got v times du, I've got 3y plus u times dv, which means I've got plus 3x multiplied by dy by dx. So this is the 3xy term taken care of, product rule. 3x is our u, y is our v, use the product rule, and whack it back in. So this becomes 4x, the derivative of 2x squared, minus, I'm going to throw this in brackets, 3y plus 3x dy by dx. Plus 2y dy by dx equals 0. Oh, sorry for the pause, that was someone knocking at the door. So this is our effectively our derivative, and we're just going to tidy this up and simplify our expression. So we have 4x minus 3y minus 3x dy by dx plus 2y dy by dx equals 0. Tidy up a little bit more. So what we end up with? We end up with dy by dx of 2y minus 3x equals 3y minus 4x. That's just simplifying this and rearranging. So therefore, dy by dx is our 3y minus 4x divided by 2y minus 3x. So we're using that implicit differentiation technique to differentiate x's, differentiate y's, bearing in mind all the laws for differentiation that we know, simplifying our expression at the end, and coming out with something that will give us the gradient of the curve. So the next thing, we're being asked to find the equation for the normal to the curve at this point. So we've just worked out that dy by dx is equal to, too many pages, went the wrong way. There we go. I'll get better at this. 3y minus 4x over 2y minus 3x. So there is our dy by dx. And we're being asked to find the equation for the normal to the curve at the point 1 minus 2. So at 1 minus 2, dy by dx equals whatever we get when we substitute those in. So 3 minus 2 minus 4 lots of 1 over 2 minus 2 minus 3 lots of 1, which is minus 10 over minus 7, which is 10 over 7. And that's the gradient of the tangent. We're asked about the normal. So gradient of the normal is just going to be minus 7 over 10. Our magic formula, y minus y1 equals m, x minus x1 will give us our equation. So we've got y plus 2 equals minus 7 over 10, x minus 1. And we're going to multiply through by the 10. 10y plus 20 is minus 7x plus 7. And then we've got 10y plus 7x plus 13 equals 0. And we're done. Now the reason I've written it in that form is only because the gradient is given as a fraction and the question doesn't specify what form to write it in. And that's it. That's implicit differentiation, and that's the ways that you'll be asked to use it. So I'm going to set you a question that's very similar to this one, and I'll pause the video. Well, I'll pause for a minute, but that doesn't mean anything to you. You pause the video to answer the question. All right, both of those questions, remember, are on the sheet that I sent around. Please pause the video and have a go at this question, and then I will show you the answers in just a minute. So I hope you did pause the video in order to do this question properly. Here is the answer. So I would urge you to pause the video if you want to check my working and work through it again. We've got another product rule in the middle there, x multiplied by y. It's more or less the same, except this time we're given the gradient, and so I substituted the dy by dx in as early as possible. You may have written it as an expression for dy by dx and then did the same. It actually doesn't matter. as long as you end up with the 2x plus y equals 0 as required. So pause the video if you need to stay with that for a little while and check your own working. Part B, find the coordinates of P and Q. We have a simultaneous equation. So we're just, again, it's almost like you could do part B without having done part A. You just make the two equations, well, not make them equal to each other, but solve them simultaneously. You get two values of x, remember plus or minus when you square root, you substitute them in, and you get your two coordinates of P and Q. Brilliant. Right, I look forward to seeing you all next week when we've got our first lesson remotely. It shouldn't be too much from me. It'll be mainly you working on implicit differentiation questions. Thanks, everybody. Cheers.